just going to start it over. We're just going to go back since I'm going to have to cut out the whole first half of the video anyway. Let's go ahead and just go back and do it again. All right, first things first. Hello, my name is Nick Larson. I am a software developer, have been for about 10 years or so professionally, and programming as a hobby since I was about 11 or so, although I didn't really get deep into it or learn anything super interesting or valuable until I got to college. Um, a little bit about me. I am writing a book. This book is about basic entry level performance. It's geared toward people who have no performance mindset. And I am using this stream to sort of talk through the ideas, get some feedback, hopefully to make it so that the book comes out a little bit easier to read and a little bit easier to understand. So that's basically what this is going to end up being. Um, I work really well in a conversational format, so please just type things in the chat. I'm constantly looking over there to see it, and we'll just sort of turn this into a conversation, hopefully. And at the end of it, maybe we'll make something that's big and nice and fun and easy to use, and everybody can learn something from it. So let's talk about the book a little bit. First off, it's a book about performance. This is not a book about a specific kind of performance. This is a book about just general performance, like in a very abstract way, and to sort of set your mind at how you should think about the different, aspects of building things. It's going to give you some really quick guidelines to go from I don't know anything about performance to the things that I build actually make some sense. And then after we're done with that, we're gonna sort of walk through some examples of how to actually, use the ideas that I'm putting here. I do want to stress that this is not, again, about a specific kind of performance. This is not about web performance. This is not about database performance. This is not about anything, whatever. The concepts that are going to be in this book are things that will carry across all of those, and you'll be able to use them, hopefully as you go on in your career and or if you just do it as a hobby, to write more efficient code. All right. Again, if you have any questions, feel free to stop me, let me know, and I'm happy to answer them. In the meantime, I'm just going to go back over all the stuff that I went over in the first hour because I clearly didn't have my mic on and no one could hear me, and that half of the video is going to be trashed. Okay, so why am I writing this book? For a lot of reasons. The first one is at Stack Overflow, where I work today. Performance is a feature. Jeff Atwood wrote a blog post about this, I don't know, maybe 6 or 7 years ago now, where there is evidence to back up that, at least people will leave your website if the thing takes too long. You might not even be able to solve a problem when you get into data science, or really into machine learning if the amount of data that you have to go into this thing is too big and you're not writing efficient algorithms. There's lots and lots and lots of different reasons why you would want to write performance code, but I think the one that stands out to me the most is that throwing away computer resources is just like a crime in my eyes, and not throwing away those resources or finding a way to use them better is super valuable. From a business standpoint, your company is also going to think that the work that you're doing is a lot more valuable because it's going to actually not cost them more money if you write performant code, right? They're either buying hardware to run the code that you're writing, or they're renting it either from a cloud provider or from whatever service it is that they're getting their CPU cycles from. However they're getting this, it costs money. By writing more efficient code, doing things that sound really trivial, like reducing the amount of time it takes to render a web request from 200 milliseconds to like 30 milliseconds, makes it so that all of a sudden you go from needing like 8 times the hardware, or really 7 times the hardware, to only needing 1 times the hardware. And that's huge. Like, that is money. You're talking about like cloud resources, cloud computing time. That stuff costs actual money, and it might not seem that expensive, but it really starts to add up. And these are like reducing the amount of time that something takes for you blinking your eye to something that is even faster than that makes a huge difference. And that's sort of the level of performance that this book is really going to be like geared around. You have these really huge tasks. There's like general ideas about how to fix those sorts of things, but for the most part, this is like when you get into the I have specified how long this thing should take, and it's taking too long, or I am using too much resources in one way or another. I need to fix that. This is going to show you basically everything you need for that. How to debug where the problem is, how to test your solutions, some really general guidelines around how to choose the tools that are going to solve your problem the fastest. All of these sorts of things are really what it's about. All right, if you have any questions, again, let me know, and I'll just keep moving on. This book, again, is for people who really don't have a performance mindset and to sort of give them an introduction to how to have a performance mindset. The big thing that comes out of this here is um, well, no, I guess I'm really gearing this toward, basically anybody who falls into that bucket. Sometimes it might be that you just graduated from college. Sometimes it might be that you just got out of a boot camp. Sometimes it might be that like you've been focusing on, web development and making games your whole career, and now you want to get into some, newer problems, some different problems. Um, this is geared toward that kind of person. If you have a large background in performance optimization, you probably will not learn a lot from this book, but it'll be good for reinforcing some things. And this book is also going to cover a very wide breadth of topics, so you might actually learn something still. All right. Yeah, I guess to sort of expand on that a little bit, the breadth of topics is really like focus number one on like instrumentation and debugging, like how to figure out where the problems are and to quantify the problems. And then second, we're going to talk a little bit about like algorithmic complexity and how to choose the right algorithms. And then after that, we are going to get into, let's just take a look at my notes, the actual tools that you use to do all of this kind of stuff. Then we're going to talk about parallelism and how you can use multiple resources to speed things up. And then after that, we're going to get into what I call micro optimizations, or really is just like using tools available at the hardware level. And it turns out that there are some of those that are so common that you can use them pretty much everywhere. All right, so that's about the breadth of this book. Now to get into the stuff that I had started with. First off, the kinds of performance optimizations that are out there. There are lots of different things that you can optimize for. When you talk about performance optimization, what you are talking about is resources and specifically minimizing the usage of some particular resource, right? This might be the number of cycles in a CPU that you use. This might be the amount of memory that you use either at peak or total, or like the constant minimum amount of memory that you're using. You might also be talking about network bandwidth, memory, bus bandwidth, all of these sorts of things. The most common one is time. People love to optimize for time, and of course the way that you do that is just get a watch out and start timing things and see what's taking the slowest, and then we work through to try and make these faster. Another really big one is power consumption, and although this one doesn't show up a lot in like your day-to-day work, if you're doing things like, I don't know, writing for Bitcoin, or some sort of blockchain technology, well, power consumption all of a sudden is going to become quite a huge thing. And in fact, there is like a shift going on right now in, I want to say, Ethereum, where they're moving away from a proof of work to a proof of something else. And the idea is that it's supposed to reduce the power consumption that it takes to like execute a transaction by over 99%. So there's all these different kinds of things that you can optimize for. It's just the different kinds of resources, and you just choose the one that you need to, whichever one is causing you the most pain. And then I'm going to show you how to like grind through and identify the problematic locations, and then we'll talk about how to actually solve them. There is another kind of performance optimization, which is minimizing peak utilization. And peak utilization is like, I have X amount of memory and I want to make sure that I stay under that, or other things have to run on this machine and I need to make sure that I don't use more than 50% of the processor. These are a different kind of thing where sometimes you'll end up throwing away the idea of reducing usage and sometimes increase usage of other sorts of resources in order to limit this one. There's a lot of trade-offs when it comes to this kind of stuff. And hello, all the new people. Please, send me messages in chat, ask me questions. I work a lot better in a conversational mode than just talking, really. All right. So that's like the different kinds of performance optimization. Then we got into talking about how to identify the bottlenecks. This is really like, this part of the book really comes down to debugging. Debugging is the key feature in like doing the performance work. The reason being, when you have a like when you have a bug, like a logic bug, what happens is it throws an exception or the output is different than you expected. And the way that you go through to like find it is very mechanical. It either tells you what the problem is in a stack trace, or you just move on and, uh, you know, step through it line by line until you eventually find where the problem is. And it's very straightforward. With performance work, it's not as straightforward. Usually they don't, you know, the usually the code still executes correctly. And what ends up changing is, it's just not meeting some specification. You're either going over that memory or you're taking too long or something along these lines. And what you have to do is you have to go through and like instrument your code in order to be able to test for the things that you care about. And as you get through and testing those, I'm going to show you how to do that. And then once you identify where the slow parts are, I'm going to give you like a framework for fixing them. And that's what 99% of this book is really going to be about. So all of these first sections are really kind of short. They will be only a few pages each. Oh, that's another thing about this book. I'm really hoping this book is going to come in right at 50 pages. Sort of jokingly, I say that because I want the book to one, be easy enough to consume in like a weekend. If you're new to this, I don't want it to feel like you're getting the whole book thrown at you. You're learning everything in one place. It's not one of those. It's like a very introductory level sort of a thing. And then second, I figure if I can write one page a week, then I can get done with this in a year. At least the writing part, maybe not the publishing part. And so that's why 50 pages is my like sort of rule of thumb here. All right, let's see. Okay, so I started off by talking about avoiding unnecessary work. Avoiding unnecessary work is pretty straightforward. You really just want to choose the right algorithms, and I'm going to show you how to do that. This is what I was working on in the background while my audio was turned off, and I'll come back around and show you that in just a moment. And then the other way to avoid unnecessary work is to cache things that don't need to be recalculated. And there's a lot of different ways that caching works. It's also very, very difficult to get right. So it's one of those things where it's like, I'm going to give you some ideas about the way that it should work, but as far as the implementation, you probably are going to end up using other tools for these. Next, we're going to talk about parallelism, and really sort of like a foundational understanding of it. Really simple. It's not going to take very long to like go through it. But just to show you how you can like move things around and how there's like a limitation to the amount of parallelism that's useful for some problems, and then really how to divide up your work to make use of parallelism the most. In this, we also talk about asynchronous code, which is not necessarily parallel. However, asynchronous code has a tool that allows you to use multiple resources in parallel that are not processors, which is another super valuable way to go. And then this last section here is micro optimizations. There's a question mark here because I'm not 100% sure of exactly how I want to introduce this. But the idea here is using processor instructions and things that are available through your hardware to improve things. And that's sort of what I want to get to. All right, so back to where I was earlier. I was writing this tool, and let's just take a look at the output real fast, which I need to rewrite a binary search. So let's not look at that. Let's look at this. So this starts off with me just giving a rough idea, this is a graph of on the bottom is input size, and then on the vertical axis is time. And if the runtime of your algorithm falls into one of these categories, this is roughly the amount of time it will take compared to all of the others. Now, what we care about here is for very large input sizes. So if you have a very large input size and the time it takes is 1, then that's really good. If it takes log n, then that's, still really good, but not nearly as good as constant time. And then we also have square root of n. At this point, we're into what's called polynomial time. Square root of n I only put on here because it shows up quite a bit for a lot of different algorithms. Then you get into linear time. This is like if you want to add all of the elements of an array, like to sum them all up. You're not going to be able to do that in faster than this amount of time. And if you want to sort an unsorted array, then you're going to be in this range for the most part. There are some other sorting algorithms that are very niche, but their analysis is far more involved than just understanding that basically sorting things takes n log n time. They're also much harder to write, which is another thing that you want to avoid. And then you move into higher polynomials like n squared. You can have like n cubed, n to the 4th, n to the 5th, n to the millionth, n to the 10 millionth, n to the 100 millionth. No matter what, it's going to stay to the right of this line at some large enough input size. So once you move beyond this, once you move beyond these polynomials, these n to the constant value, and you move to some constant to the n value, you're now in exponential land. And in exponential land, what you end up with is really, really, really slow running times for just about everything. And then above this, there is one more level called factorial time. And these sorts of problems, you cannot solve very large instances of these. Maybe as many as n to the 100, maybe n to the 200 in some cases, and beyond that, you are pretty much stuck if your algorithm actually takes that amount of time. So you're just not going to be able to do more than that, at least not using the algorithms and the programs that we have available and the hardware we have available today. So the general idea here is don't worry about how to calculate these things for any given algorithm. However, what you should know is that you can go and look these up for any given algorithm. And the idea is that you want to start up here and move for your problem as close to down here as possible. And the closer you get to down here, the faster your algorithms are going to run. And that's just the way it works. So let's take an example. The example was I have two arrays of integers, and I want to compare if any element in the first array, if any element in the second array is in the first array. And we came up with 3 different ways to do that. The first way was what I call the naive way, or the n squared way, which is for each element in the first one, or rather for each element in the second one, you see if it's in the first array. And the idea here is you have to look at, for each element in the first array, you have to look at each element in the second array. And we're counting the number of comparisons here so that we can see the actual differences in the amount of work that these things need to do. So we have comparisons. So for each element in the first array, we look at each element in the second array. So let's just, for the sake of argument, say there's 5 in the first array and 5 in the second array. Then for that first element, we have to look at 5 elements. Then for that second element, we have to look at another 5 elements. So we're at 10 elements. For that third element, we have to look at another 5. So we're at 15. And it just keeps going up like that. And so you take this number times this number, and for the sake of argument, for this example, we're just calling that n exactly one time. I should just call this n. N, 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 and n. Okay. So for this input size, we're just making both of our arrays the same size. And let's not do this, call these int arrays. This is going to save us just a little bit of trouble later. Instead of doing it very generically. All right. Okay. So for this one, what we have to do is we take, the number of times, the number of elements in here times the number of elements in here. And that is going to get us to our solution. The next one, we do an n log n solution. The way that we do n log n is we first order the first array. And remember, I told you that ordering takes, if I can find it, ordering takes n log n. So we're already below this n squared for the first step. And now for the second step, we're going to go over n items and we're going to binary search them. So we're going to do log n steps for every element in the second one. So this is n times log n. And what I need to do is actually rewrite this binary search, which we'll do in a few minutes, to output the number of comparisons that it actually did instead of just calling it one comparison. And then we look at a way to do this in what's called linear time, or just using big O of n. And as we see again, that is here, so that is even better than this n log n. The way that we do that is we create a hash set. Now a hash set is a data structure that, if you're not familiar with it, allows any item to be in there exactly one time. That's what a set means. And a hash set means that we're finding the location of it by hashing the value. So for each value in first, we are hashing it, and then we're storing it in the hash set. And that takes, hashing takes a constant amount of time, so big O of 1. And then we are doing that for n elements. So n times 1 is n. And so this step right here takes big O of n. And we should actually, for the sake of argument, put that as n. Our first dot size dot count dot length. There we go. And for this one, we should do int n equals first dot length, and then we do ideally we would write the sort by ourselves so we can see how much work that takes as well. So I think we'll just add that as a to-do actually. And for now, we'll just ignore these first comparisons. 0. So to do count hashes to create hash set. And then we'll do a to do up here, which is write sort to count comparisons. There we go. And then to do here, write binary search to count comparisons. Okay. All right. So now back to this, we have a way of doing this in linear time. So we are creating a hash set, and that takes big O of n time, so linear time. And then we have, for each of the second one, we're going to check if the hash set contains it. Now the way that you do that is you hash the item, the value rather, which takes big O of 1, and then that hash value tells you exactly where in the hash set to find it, so you can check this contains in big O of 1 as well. So now we have, for every n, we're doing n work. We're not doing anything more interesting than that. And what this allows us to do is very, very quickly find the item and determine whether or not it's in the hash set, so big O of n. Now what we want to do is we want to implement this binary search real fast instead of just using the built-in one, so that we can count the number of comparisons. And then what we're going to do is run this to sort of show you the output that we're looking for. Is given an input size of 100, how many comparisons do we have to do for this algorithm, for this algorithm, for this algorithm, and then for all of these different input sizes. And as you can see here, even getting to 100,000 elements, you have to do a ridiculous number of comparisons in order to figure out whether or not the element is in there. And since it's not, 100,000 times 100,000, we know that there is a match. And so it's still quitting early, and that's how long it was taking. So let's go ahead and do these other binaries. Let's implement this binary search real fast. Public int binary search. And what we want is int array sorted and int object, item rather, value. Sure. All right, return -1. That's going to be the last case. So now what we want to do is change this to, I think we're going to return this as a tuple. And this is going to be a named tuple of index and comparisons. And then we're going to return -1 and sorted dot length. All right, and now what we'll do is we'll say int c, int c equals binary search of sorted first and j. And now we're going to say comparisons plus equals c. And I guess instead of doing that, we should just do this as a long. Comparisons long. And then I wonder if you can do var. That'd be really awesome. Ooh, that's awesome. Okay, and then we say if I is greater than or equal to that, then return comparisons. Okay, so this is sort of where we're at. We've now written a binary search. No, we haven't. We have to actually implement the binary search. All right, how does a binary search work? This is one of those things where it's like, let's just go look it up. C# binary search. Binary search. Okay, there we go. Just save us the time. Copy and paste this almost verbatim. Int while, call it sorted. I think I got too many here. Oh, I think I want to increase these. Okay, mid equals min plus max divided by 2. This is all integer math. Okay, key equals sorted of mid. Key is not defined. Int key. Oh, no, value. It wants value, okay. Value. All right, if value is less than, return plus plus mid. That is an awful way to do that. That doesn't return that. Why on earth would you? You want the index. That's what I want. I want the index. Mid. Mid. And compare long comparisons equals 0. Comparisons plus plus comparisons. All right, not input array, but instead sorted. Man, all this white space. Okay. Okay, that gives us max is mid minus 1, min is mid plus 1. For the sake of argument, I'm just going to assume that this is correct. And I don't want sorted.length, I want comparisons. There we go. Now let's run this again. Okay. So what we end up with is, what do you think base 2 of this is? So 2 times 2, or rather clear, let's go, is there a log? Is there a log base 2? Of course there's not. Let's just go to one of these. So 100 log 2 of 100 equals 6.6. So we claimed that there was going to be n log n, and what we see is that what we should have gotten is 100 times 6.6, but instead we got 100 times 7.7. Probably what's happening here is that last level really matters. And I bet if we like modified the way that we think about this a little bit to include that, then it would, I don't actually know how to, so maybe log 2 of 100 plus 1. Yeah, 7.6, and this is right on with it, with where we would expect it to be. Let's see if this holds true for the rest of these. So no. So this one's times 7.7. Oh yeah, we got to change this. So log 1000 plus 1 is 10.9. Oh, and guess what? That one came out almost exact. And then for 10,000, we have 14.3. Yeah, that one's right on pace. And then for 100,000, we have, well, this one is a little bit different. So the reason that this one is different is because we actually found the element that is in both of them, right? Because these don't go all the way to 10,000 means that the 17,590th element was in the first array. And because of that, we cut out short. So what we would do is we would run this a bunch of times, maybe 10, or if we were doing some sort of benchmarking, we would do it even more than that, maybe 100, maybe 1,000. And what we would see, see on this one, the 10,000th element was in there. And if we do more and more and more, we do more and more and more, what we'll see, there we go, this one seems to not be in there at all. Yeah, this one seems to not be in there. Now, why is this taking so long? Yeah, there we go. And it was in there. Crazy. But it still was much further out. Let's go up. 10,000. That's crazy. Look at how long that takes. Like n squared is just a huge number. When you get into polynomial time, like you want to avoid that. That's why we're trying to, again, crawl down this as much as possible. We want to, you know, most things start out over here or somewhere in this range, and we want to push them down as far down this path as we can. And this is where the vast majority of your performance is going to come from. And you can see that right here, this one example, this super naive way of doing something that's actually quite common, comparing if, you know, one element from one array is in an element from a second array, can take a very long time when done naively for a trivial size input. Like 100,000 is just not a large input. You should be able to do things with 100,000 elements very, very quickly. All right. So that's kind of the idea. Again, don't worry about how all of this is calculated. The goal is just to push things further and further down this chart. And that is really the key to like the first part here, which is choosing the right algorithms. So let's talk about a couple of things that actually fall into these categories. Hashing is big O of 1. In fact, I'll just start making a list here. Hashing is big O of 1. Let's array lookups. Array lookup by index is big O of 1. And that's about it for now. Log n, this is binary search is the big one here. Anything that you can do a binary search on, you can do in log n time. Give me 1 second, I'm going to cough. All right. For square root of n, I don't have anything off the top of my head, but I know there are things. Oh wait, no. One thing that sticks out is if you're doing jump list in like say, so square root of n tends to be like asymptotically best when you do things like how far ahead can I look without skipping too many and having to come back more. So instead of doing a binary search where you're cutting everything in half, if you know a little bit of the distribution of your list, jumping ahead, I'm not even going to go down this path because I don't have an example. All right, big O of n, this is things like counting the number of elements, counting things. Wow, that was awful. How about we just move that over? Yeah, counting things that are in an array, going through an array index one by one, these sorts of things, going through the characters in string, cars in a string, these sorts of things, going one by one through anything, that's what big O of n turns out to be. Big O of n log n, sorting by comparison. Sorting by comparison. This is when you take two elements in your list, you compare them together, and then you make some decision about whether or not to swap them. Sorting by comparison takes, big O n log n. Now, there are faster ways to do it that are not by comparison. Most of these are done by counting. However, it turns out that it's very easy to write these, and they're just wildly efficient. There are some interesting things that we'll look at when we get further into the book, but for now, just know that like sorting things takes about n log n. And then polynomial time, lots and lots of stuff takes polynomial time. Almost everything. The kind of stuff that takes polynomial time, that like actually takes polynomial time, is like matrix multiplication. Basically any linear algebra, I shouldn't say any, I'll say matrix multiplication. And this is something that we're going to look at in detail. Matrix multiplication turns out to be something that you do on a computer all the time, and we can make it really fast. And that's one of the things that we're going to do. We're going to start off with what seems like, the obvious implementation. We're going to talk about a way to actually push down the complexity, and it turns out that that's not a great solution for matrix multiplication, which is a topic for later on. Okay, so pushing things down, this is the sorts of things that fall into these different categories. Now what we want to do is move on to talking about other ways to comparing graph algorithms with large inputs. Yeah, so this is usually used when the amount of data that you have to input is quite large, or the amount of work that you have to do per data input is quite large. To give you an example of something that actually takes quite a long time to do, the naive way would be like a Fibonacci number calculation. The Fibonacci number is based on the previous Fibonacci number and the second previous Fibonacci number. You just add them together. And then they have the base case of 0 and 1. So you start off with 0, you start off with 1, your next Fibonacci number is 1 plus 0. Then it's 1 plus 2. Then it's 2 plus 3. Then it's 3 plus 5. Then it's 5 plus 8. And it just goes and goes and goes and goes. And if you don't actually store the number and you do it very naively, then you're in this land, in this exponential land, in order to solve this. And it turns out that's, obviously not that good. But you can get it all the way down to big O of n, in a sense. Up to a limit, you can get it down to big O of n. Okay. Common. All right. The other major topic in this area is caching. We'll just go over some of this stuff for about the last, 20 minutes or so. Caching is a very common technique used for a lot of different things. The one that you use in code usually, like as part of an algorithm, is what's called dynamic programming. And dynamic programming works by storing the results of past computations so that you don't have to recalculate them when you need them again. We'll go into a couple examples of these later, but for now we're just going to move on and talk about other kinds of caching. Another kind of caching is pre-calculation. Pre-calculation comes in a couple of different forms. First is like static generation. This is like my website, cultureofdevelopment.com. There is like an actual tool back here that I use to write all of this stuff in. It's written in Markdown. All of the links here are generated, via some variable in code somewhere. And then I've got all of these other things that are all generated at the time that I say generate them. And what it does is it basically builds all of these HTML pages one time. And then I just export those HTML pages to my website, and those things get loaded up very, very quickly instead of having to reconstruct the page every single time somebody comes to it. That is one very common way, and that's called, again, static generation. There's another kind of static generation, which is what I like to call code generation. And this one shows up, less often, but it can be quite good as far as improving the runtime of your code, because instead of having to do things like figure out what sort of element is coming next in a JSON object, you just tell it beforehand, expect this, and then if that doesn't come, you throw an exception, right? This sort of thing where you are pre-telling something what to do and then writing code exactly for that thing is a form of pre-calculation. Like I don't have to do that work later on because I have already done that work up front to tell it what to expect. All right, and then model building. This one happens all the time in things like machine learning or AI. The idea is that like you want to build some predictor for something. What ads should we show to somebody on this website? And what you do is you build a model for that. You say like, here are my inputs, here are my outputs. I have built this model. All I now have to do is run the model on my new inputs and I get my new outputs. Instead of having to calculate all of the model every single time I want to run it. Now, if you only have a little bit of, data that's going into your model, then maybe you do want to rebuild it every time because you might be able to get a little bit, there might be some fancy tricks that you can do here and there for tweaking specific things. But the general idea is that you pre-calculate everything that you can. When a user comes to your site, you should not have to look up all of their previous history. There should be just a values that you go and load from somewhere that you have pre-calculated for that person. And then you run them against your pre-calculated model to get an answer very, very quickly. And we will see an example of that that's related to the last thing that we're going to do. Another thing is like general caching. And this is when you have content where it's okay that it gets a little bit out of date, then you can cache it for some amount of time. This would be things like if you're going to Stack Overflow, for instance. Stack Exchange, I did not mean to do that. And if you go to Stack Overflow, for instance, and you go to a page like this as an anonymous user, let's actually just go do that. New incognito tab, Stack Overflow, and then you go to a new page. Almost all of this is pre-calculated. Like these things right here, these linked things, pre-calculated. Hot network questions, pre-calculated. The whole page itself, pre-calculated. And because I am not logged in, it does not need to show me anything up here that is specific to me. So what it does is it just stitches together all these pre-calculated things and then creates a page and stores it. And that's it. It just leaves it. And it'll keep it there for, I don't know, say 10 seconds, maybe 15 seconds. And the next time you reload it, you'll actually see if anybody had done anything interesting with it. And that is another type of caching. All right. Okay. Another kind of unnecessary work that happens all the time and is the source of a lot of performance issues is memory allocations and garbage collections. These are specific to the language that you're running in. The memory allocations, are normally the large groups of memory allocations are normally due to, I'm sorry, not allocations, of collection. Okay. On one side, you have memory allocations where you're like saying, give me a bunch of memory. And then you have on the other side, okay, I don't need this memory anymore. The way that garbage collected languages work is you ask it for a bunch of memory and then you release it when you want to, but it doesn't actually release it. It waits until some magic time and then it goes and it releases it all at once. Sometimes to catastrophic, failure modes. Very, very long pauses, stop the world kind of stuff. Memory allocations, it turns out normally you can get around these by just creating, pre-allocating a large amount of memory in set sizes and then asking the system for, one of the pre-allocated bits of memory. And allocating memory normally goes to the operating system, and the operating system eventually is the thing that's like, okay, here's your little bit of memory and here's the location that it's at. And then it has to do a lot of work to, one, find a free place in memory that has the amount of size available that you want. And then sometimes it has to move other memory around as part of it in order to like give you that, to make enough consecutive free space in order to give you that. And then garbage collections, there are lots of ways to solve garbage collections, but again, they have this stop the world property and a lot of different implementations that will cause like your entire system to hang for maybe as much as a second in some cases, depending on how much stuff you're getting rid of. Um, and so we'll talk about, some common ways to get around that. I am much better with this in .NET land than any other land, so that's what we're going to focus on when we get to that point. All right, the next major topic is dividing up the work, doing things in parallel. So to give you an idea here, let me go ahead and save this right here to make sure I don't lose this thing that I built. Culture of development, and then we're going to put this in my books, perf book, and we're just going to create a new folder called random stream images, and this is going to be called time complexities. Okay, now let's get a new one here. Sure, 800 by 600, whatever. Okay, and now what we want to talk about is like parallelism. So there's a few kinds of parallelism, but the idea is that you want to make use of multiple resources at the same time. Let's say that, just giving you like a really brief introduction here. This is not like the final stuff, but the idea being that, like, let's say that some of your data is stored on a hard drive and some of it is stored on a totally different computer somewhere else on your network. And what you need to do is go and get that data, load it onto your system so that you can then do whatever you want to do with it, right? When you go tell your hard drive to give you something, it takes forever. Like, to scale this up, there's some people who have written better things than this. Scale of getting hard drive data. No, hard drives. Time to access different memory. Approximate. Yeah, I want to say this is going to end up being it. No. There's just like an image that I want to show. And I should have had this available. Yeah, this is sort of it in terms of cycles. Okay, so this is sort of the thing. This appears to be, let's just go to the site. Register. All right, of course, open image. Open image in new tab. Please tell me it's bigger. No, we'll just zoom in. All right, so the idea here, if you scale up a reference to like a register to be 1 second, then to go and like look for a really fast SSD hard drive takes days. Like, that's how long it takes to go and talk to a hard drive is compared to talking to a register on your processor. It just takes an incredible amount of time to go and get that data. And that is, I don't know how many seconds are in, well, yeah, I don't know how many seconds are in a day, but I'm guessing it's like 80,000-ish. And that means you have 80,000 seconds worth of computation time, scaled accordingly, that you are not using your processor while you're waiting on that. And you should be using your processor because that is free resources. It's just sitting there waiting. It's spinning and saying, is my data ready? Is my data ready? Is my data ready? Is my data ready? And it's saying that hundreds of thousands of times for it to go and get that data from that disk. So what you want to do is fill that time. And the way that you're going to end up doing that is by running your data access in an asynchronous fashion. And that asynchronous basically is a way of saying, like, okay, I have told this other thing to go do some work, and in the meantime, let's do this until that thing tells me that it's ready. And when that thing tells me that it's ready, then we'll go back and we'll do that. And that is going to allow you to keep using this resource. So this is like an instance of wasting a lot of time and also wasting a lot of like computational resources. You can improve the time that it takes by working on the data that comes in while you're waiting for the next bit of data to come back. You can increase the time by kicking off some other process and saying like, okay, now I'm going to go and work on this other task real fast and then come back. Or you can, you know, basically whatever you now have this resource, available again. And so we're going to use asynchronous code as basically our means of going off and kicking off all of these other things that take time. Doing a network request, that takes time. If I go to Stack Overflow, it's going to load very quickly. Stack Overflow. It's going to load very quickly, but it took my computer some amount of time to make this web request and then actually get the data back and then start doing stuff with the data. That free time the computer has available to do other stuff. And when we're talking about time scales on the order of milliseconds, then those freed up milliseconds are going to be quite important, especially on things like, a web server that's dealing with, 100,000 hits a minute or so. Okay. The other thing is, and I don't really want to get into this now, but I'm just going to give you like a brief overview. Let's say you have multiple processors, right? So the general concept that I want to like dig into on this part of it is really just like, let's just do red. Generally, the way that you organize things, how do I get to my layers? Add a layer. Generally, the way that you organize things, when you have something like this, or like tasks to do, is on a single processor. That's a good idea, actually. Let's go ahead and go back to blue. Let's go back to black. Just make one processor line. Give me a new layer here. All right, when you have a single layer, when you have a single processor, you tend to organize your work like this, where you have task 1, then you have task 2, then you have task 3, then you have task 4, task 5, and I just can't seem to get rid of it. And then task 6, and then you're done, right? But the reality is that what actually happens is you have connections of dependencies between these different steps, right? You can run this one, and then you can run that one. And then at the same time, you could be running this one. It doesn't matter which order you put these in because they're not related to one another. And then you have this one right here is dependent on here. And then you have this one right here is dependent. Okay, let's redo that. And then you have this one right here is dependent on this. And then you have this one right here is dependent on this. And this one right here is dependent on this. And then now you can exit. Now, imagine for just a moment that, no, let me, and let's just have 2 going out of here. And then this right here. And this right here. Okay, so the idea being that, okay, now let's assume that you actually have a second processor. In the case that you have a second processor, this can actually change, right? We could move this work over here and then move all of these down 1. Or we could move this work over here and then let's just kind of see what we can end up with. It'd probably be easier if I drew this on the board, but since we're on this, I'm just going to stick with this for now. Let's go ahead and have two side by side. And we're going to draw the exact same graph. We're just going to split it up so that, and I guess we should do time steps. Can I do a dashed line? Dotted lines. Okay. And then what I want to do is get this like yellow line, not that yellow line. I want this one to be a yellow line. And I want this to be dashed. Okay, these are what we're going to call different time steps. All right, these are different time steps, and this is a one processor scenario, and this is a two processor scenario. Now what we're going to do is we're going to take this work and we're going to split it up across these two to show that you don't actually need all of that space. You don't need to actually take 1, 2, 3, 4, 5, 6 time steps. You can get the work done in fewer time steps. Right? We have this, then we have this, and now we have this. And if we take our blue again, solid. Okay. Make it solid again. Take this, take this. All right, so we have now done this and this. And so we have these three items in the first two time steps. Now it doesn't really matter how we break things up, but for the sake of argument, we're going to move this one over here and this one over here. So I need my boxes back. I need to go back to red. Okay, go back to here. We're going to say that this one is this one, and this one is this one. So this one comes out. Go back to blue. So now this one comes out of here and goes to here. That's this one. So this one is this one. And then we can do this one as well at the same time. And then we can have just this one red box at the end. And we draw our line that goes from here. Don't want that. Draw our line that goes from here, and from here, because this last one depends on all three of those. But what we did by using two processors is we reduced this thing that took 6 steps down to only taking 4 steps. And that's sort of the idea. And I'm going to show you how to sort of understand that and a lot of the nuance around it, so that you know when it's a good idea to try and break things up in parallel and when it's not a good idea to try and break things up in parallel. And that's it. Let's go ahead and save this as well. And we're getting right to the end of the stream here, as difficult as that has been for me. But we're going to just keep doing it anyway. Let's go save. Random stream images. Yeah, we'll just keep it as a PDN. Okay. So that's pretty much it for today. Learned a lot about streaming. As far as some mistakes that I was going to make, and I'm glad that I got those wrapped up. Second thing is I learned that I probably need to focus in a little bit more or practice a little bit of the stuff that I'm going to say. And the third thing that I learned is, I don't know. It's hard. That's all I can say. But it was fun. I think it'll be a little bit more fun once more people start watching. And in the meantime, yeah, just I guess get ready for next week. We're going to look at. I got to get a calendar up, but in the meantime, um, yeah, next week Twitch.tv, Nick Larson. In the meantime, yeah, next week we're going to look at profiling. So that's what we're going to do. We're going to do a little bit of the like adding in some timers. We're going to do a little bit of like seeing how easy it is to measure the different things that you need to measure. And then to sort of, show you the process of narrowing it down to find something. So we're going to start off and I'll have some code that is not great. And then we're going to add in some tooling and we're going to slowly but surely change things to make it better. And we'll go back next time. We will also use the sort of algorithmic fixing that we talked about here to write some improvements to the tool that we're going to work on. All right. It was good. Thanks everybody for watching who was here, and see you tomorrow.